Finished network layer today. It's just a couple more things. Okay, so we've completed the routing algorithms, right? And we also talked about BGP. I think we were at this point here. So we talked about routing link state distance vector, and then we talked about the autonomous system concept, where within an autonomous system you have a routing algorithm and between autonomous systems. And I think some of you came and talked to me. Typically, within an autonomous system, you can use things like link state, like Dijkstra. But between, you typically cannot, right? So distance vector is used there. So everything we've been talking about so far is point-to-point, unicast, single sender, single destination. Okay? I want to end by talking about, in the network context, broadcast and multicast. So in broadcast and multicast, you have many senders and many destinations. Okay, so broadcast routing. So we'll typically talk. It's enough to just talk about single source, many destination, because many source, many destination just scales with the number of sources. Okay, so it's enough to just say what happens if you have single source and many destinations. So in the broadcast case, if you have a single source, let's say R1 is a source of data, and let's say R2, R3, R4 are the possible destinations, right? So you could clearly set up three unicast connections, R1 to R2, R1 to R3, and R1 to R4. So that's a solution to the broadcast problem, is multiple unicast connections. Remember, unicast is from one source to one destination. Now, do you see a problem with the left picture? We're setting up multiple unicast connections. What's the problem? Do you see a possible inefficiency? Yeah, what is that? Yeah. Right, the packet is sent through R2 three times. So in fact, there were three transmissions to R2. I mean, the transmissions to R2 to R3 and R2 to R4 have to happen. But there's three transmissions to R2. We can fix that by asking R2 to forward the packet. Right, so that's one way of doing this. So it's called in-network duplication. And this is how sort of one reasonable, straightforward solution to making broadcast efficient. But of course, this has a lot of problems. And the biggest problem is flooding. Right? So imagine a rule which a router says, any packet that comes in my network interface, I forward. Well, you could end up in what's called a broadcast storm. If I get that packet again, I'm going to forward it, and so on. Right? So you can try to control that problem by doing control flooding. So you only broadcast packet if it hasn't been broadcast before. Right? So you could have rules like that. Yeah? Yeah, excellent point. How do you know? You have to keep track. So that's the problem with controlled flooding. I need to now maintain system state. Absolutely. So flooding, I don't need to maintain system state, but it can lead to sort of overwhelming the network with lots of duplicate packets, and you don't know when to stop. Control flooding, you have to keep state. Okay, so the real solution is to create a spanning tree. Okay, and when you create a spanning tree, you just do flooding on the spanning tree. And since there are no loops, you won't get a broadcast storm. Okay, so that's how we do broadcast in a network. Okay, you construct a spanning tree and you flood on the spanning tree. So there's a broadcast and multicast are almost the same thing. In broadcast, every node is a destination. In multicast, not every node is, but there's multiple nodes. So they're almost the same thing. Okay, so a few ideas. So I think the creating spanning tree. So we already know how to create a spanning tree. Does anybody I know you must have talked about it in part 1, right? Did you talk about spanning tree? No, yes or no? Okay, you didn't. That's fine. But we did in our half, right? What? How? Like, what was the algorithm to create a spanning tree? Yeah, Dijkstra, the shortest path algorithm, Dijkstra's algorithm creates a spanning tree. So we know how to create spanning trees. Okay. So for example, if I have this network here, I've shown you the network on the left is a network of, let's say, 2, 4, 7 nodes. The dark edges are the edges in my spanning tree. The light edges are edges in the network, not part of the spanning tree. Okay, so this is a possible spanning tree. This spanning tree happens to be rooted at A. You can have multiple spanning trees. For example, this spanning tree is one. So I'm using the same spanning tree, but here the broadcast is initiated at D. So once you have a spanning tree, right, you have a path from one node to every other node. So you can have the broadcast happen from any node. So that's how you get multiple source, multiple destination. All right. The thing I want to point out here is not every spanning tree. So this is the same spanning tree, but spanning trees are not unique, right? Like for example, can you look at this graph and create a new spanning tree? Like, can you remove an edge and add an edge to create a new spanning tree? Give me an example.
Remove the one from C to E and make it from F to
Yeah.
yeah.
Yeah, or add the one from D to E, right? Yeah. So the only point I want to get across is spanning trees are not unique. In fact, if you want to count the number of spanning trees, do you happen to know in the worst case what's the number of spanning trees? It's going to be exponential. Essentially, there's an exponential number of spanning trees. Because you can think about it this way, every edge is either in your spanning tree or not. Right? But of course, many of those are not going to be trees. Right? But roughly that set scales as 2 to the number of edges. Okay? So there are a lot of spanning trees. Okay? So the point I want to make is that there's the idea of a good spanning tree. Now, in this example, I gave you a spanning tree rooted at A with the broadcast at A. So this is most likely the shortest path spanning tree from A. But remember, when we did Dijkstra, we computed the shortest path spanning tree, or we computed shortest path route from U, the source, to destination. But what did we get? For free, almost free, we got the shortest path from the source to all nodes. Even though we only cared about the destination, we got the path to all nodes. That's why it's the shortest path spanning tree. So this is likely the shortest path spanning tree from A after running Dijkstra. So it's good for A, but as I said, you can do the same thing for broadcasting from D. Now this is not very good for broadcasting from D. Can you see why? Because, for example, to get from D to E is a very long path, but D has a direct connection to E. Okay, I'm just pointing out that there are many spanning trees, and you might want to think about which spanning tree you want to use. Okay, so the goal in broadcast or multicast routing is to just find the spanning tree that contains all of the nodes that you want to connect. Okay, now I'll point out that so you can have a source-based tree, which is if I know, for example, one node is a source, I can construct a spanning tree from that source. If you're going to have multiple sources, right? You may want to take another approach, which is what's called a shared tree. A shared tree is going to be a tree in which you have multiple sources, and we saw that a tree based like tuned for a certain node may not be good for other nodes. Like, for example, here, a tree rooted at A is not necessarily good for broadcast from D. Okay? All right, so I think we already know how to construct the shortest path tree. We can just use Dijkstra. Okay? So that brings us to the idea of a shared tree. So a shared tree is a spanning tree that's used by all the nodes. and so I want it to be good for all the nodes. Okay, and the tree that's good for all the nodes is called the minimum spanning tree, or the Steiner tree. Okay, and sometimes it's called the minimum cost spanning tree. So remember, edges have labels, and a tree consists of a bunch of edges. So the cost of a tree is the sum of the edges in that tree. Okay, and the idea is that if the tree includes low-cost edges, it's going to induce low-cost paths for all nodes. Now remember, it's not going to be optimum for any node. But on average, if every node can be a source, it's going to lead to, on average, lower cost paths. Okay, so this is it's called the minimum cost spanning tree, or the Steiner tree. Finding the minimum cost spanning tree is actually NP complete. Okay, meaning that it's a hard problem to solve. Do you guys know what NP is? NP hard and NP complete? Have you come across these terms? No? Okay, so NP complete stands for, these are sets. They are sets of problems, okay, for which we don't have efficient solution. But we can check the solution, that a possible solution is a solution efficiently. But we cannot compute a solution, or we don't have a known algorithm for computing the solution efficiently. All we have is a brute force solution. For example, in this case, the brute force solution is compute all trees. Compute the cost of all trees and pick the smallest one. But we already argued that the number of trees is exponential in the number of edges. So your complexity in finding the minimum spanning tree is exponential in the number of edges. And that's not very efficient if you have a lot of edges. Okay? So that it doesn't mean there does not exist a polynomial time solution. It just means we don't know if it does. And this set is a set of all problems for which, if you know the solution to one of them, you know the solution to all of them, because they're transformable into each other. So like this set, NP complete, consists of a bunch of problems. All those problems are effectively the same problem, because there's a polynomial time transformation between all these problems. So one of the biggest questions in computer science, or let's say in math, science, whatever, engineering, is P the set of problems for which you have a polynomial time solution, a fast solution? Is that equal to NP? Right? You've heard of this, right? Does P equal NP? That's the question, is do we have good solutions to these quote-unquote hard problems? So this is a hard problem, but we have good approximation algorithms to solve this problem. Okay? We can get close to the optimal solution with a provable guarantee. Okay, so with this, I want to end. I think that's the last slide I have for multicast. Yeah. Okay, so we've kind of covered all of routing of network layer, right? Starting from the very beginning, talking about IP addressing and so on, through routing algorithms, to unicast routing, to multicast routing. And it turns out that the core of the broadcast or multicast routing is still Dijkstra, right? Which is algorithm for finding the shortest path from a given node to all other nodes. Okay, so you should now be able to at least do homework 3. I'll be around for as long as you need today if you have questions about homework 3. And again, I'm very, very sorry for starting class late today. Okay, when we come back on Monday, I'll talk about the YouTube hijack, and we'll do problem solving. Okay, remember your homework is due on Sunday. I will also release the homework solutions on Sunday night. Okay, so please submit your homework by Sunday. I'll release all the solutions. You have a quiz on Wednesday, right? I'll also I'll give you a sample quiz. Okay, I'll do that on. I think I owe you that. All right, I'm going to give you a sample quiz. I'll upload that on after the homework on Sunday night. All right, so if you have questions, I'm around. Thanks.